Welcome everyone to the SIMBa seminar. Today we are having Eva Philippe in our seminar. She's doing a PhD in Paris. I will not say the university, but she has joined our community here at UB during a year. And today she will be talking about regular subdivisions and triangulations. So.
Yes, thank you very much for the organization of this very nice seminar, and to all of you for being here or online. So I wanted to present a bit to introduce you to my area, polyhedral combinatorics. So it's at the intersection between combinatorics and geometry. So for me, the geometry I do is Euclidean geometry. Okay, so just R to a certain dimension D. And I chose this topic of regular subdivisions because they appeared a lot in my thesis. And so my plan is to give you a bit the basic definitions, the basic objects, and then show you 2 or 3 examples of why these are particularly nice objects to look at. So my first definition is a polytope. These are my favorite objects in mathematics. Is the convex hull of a finite set of points. Okay, so very easy definition. We take a finite set of points in our space R to the D. We take the convex hull, so let's say in the plane, we have points. So what does the convex hull look like? Let's put the interior. And you have a polytope. Okay, there is also another definition, but I will not need it. And so this is the geometric object. Also, the easiest examples are simplices. Obtained if my set of points is made of a finely independent point. So this in dimension 2, I could have the triangle, in dimension 3, the tetrahedron, and so on. Very basic examples. And so these are very geometric objects. I mean, I have precise points with precise coordinates, and the combinatorics is obtained with their faces. So the face of P is the set of points in my polytope it's a subset of my polytope that is maximized in a certain direction. So this is, we recover the classical notion of faces that you know for polygons. So for example, if I choose this direction, I will have this whole edge. That is the face of my polytope. If I choose this direction, I will have only one point. So the faces of dimension 0 are called the vertices of the polytope. If I do this in higher dimensions, I will have also faces of dimension 3, 4, and so on. 2, 3, 4, and so on. Up to dimension d-1 if my polytope is of dimension d. And also, if I take the direction 0, I'm maximized on my whole polytope. So I also consider that the whole polytope is a face. And by convention, we also add the empty set as a face. So if we look at the set of all faces of my polytope, we have the face coset of P. So if we want to do this example, we have, so cosets mean a partially ordered set. We can order the faces by inclusion. So we have the two-dimensional face, then we have 5 edges and 5 vertices and the vertices, and so this is the classical drawing. Okay, but maybe you understood the idea that we represent the cover relations, the minimal inclusion relation. Okay, so now we have this combinatorial structure, and this is what we call the combinatorial type of our polytope. So you see that in dimension 2, it's not very interesting because it's only given by the number of vertices, which is the same as the number of edges. So in dimension 2, we have the bijection between the combinatorial types of polytopes and the integers, and that's it. But of course, it becomes more interesting in higher dimensions. So for example, in dimension 3, it's a bit more interesting, but still we understand very well what are the possible combinatorial types of 3-dimensional polytopes, because in fact they are only determined by their graph. So only the data of the vertices and the edges allows us to recover what can be the 2-dimensional faces. And so the graphs that appear as graphs of polytopes of dimension 3 are exactly planar 3-connected graphs. So we understand quite well the dimension 3. But in dimension higher than 3, just starting at 4, things become much more complicated because we have no combinatorial characterization of which posets. So the posets that arise as face posets of polytopes are very special. For example, they are graded by the dimension of the faces. There are also what we call lattices. There are atomic, coatomic, anyway. So they have special properties. But even if I give you a poset with all these special properties and I ask, is it the face poset of a polytope? Is there a geometric object such that this poset is its face poset? This is NP hard. In fact, it is as hard as determining if a certain system of polynomial inequalities has a solution. So just to say that, okay, the definition of polytopes is very simple, but still there is complexity arising. Another example is that just counting how many, if I fix the number of vertices and the dimension, how many combinatorial types of polytopes are there is also a very hard question. Maybe we will come back to it later. Okay. I forgot to say that if you have any question at any point, please ask. So these were the polytopes. Now subdivisions. Okay, I will. So the idea is we subdivide our polytope into pieces. We partition the polytope into pieces, and with certain rules. So I will not write down the precise definition, but the things we want to forbid are this kind of behaviors where we have sub-polytopes, but they do not intersect nicely because they do not intersect in the face of another polytope. And also, we want to know which vertices we allow for the sub-polytopes of the subdivision. So this is not a valid subdivision, but if we want, we can still add a point and say, now we are not subdividing just the polytope given by its vertices, but a point configuration. So we are also considering point in the interior of the convex hull, and then now we can still have, this would be a valid subdivision. Okay, it's very quick, but we will see other examples. Yes, maybe I will draw some examples. So I start with this point configuration made of two equilateral triangles, one inside the other. And I can take the subdivision where I take all these points to be one cell of my subdivision. So if I take the convex hull, I will have this big triangle, but I also want to mention that I take these 3 points, and then to be a valid subdivision, I will take all the faces. So this subdivision means I take one cell that is given by these 6 points, 3 cells that are given by 2 points like these edges, and 3 cells that are just the 3 vertices, and the empty set. Another subdivision of the same point configuration would be if I do not, the biggest cell here will be only these 3 points. I do not take the points inside. This is also a subdivision, and then the other faces are the same. Another subdivision, maybe more classical definition of image of subdivision would be this one, where the maximal cells are 2-dimensional, and we have like 3 quadrilaterals on this triangle and all their faces. And finally, okay. And also, this one is a triangulation because all the cells are triangles. And also this one, because so the maximal cell is this big triangle, so it's also a triangulation, but not this one because we have too many points. In the B cell, we have the 6 points. Okay, so is it okay with the notion of subdivisions and triangulations? So in higher dimension, the cells have to be made of finally independent points. The equivalent. Okay, so but in my title, it's regular subdivisions. So even if I have not written down the precise definition of subdivision, I will still be precise about when they are regular. So I say that a subdivision So I'm considering a fixed point configuration, and when I say that I take a subdivision of it, it means that I have a collection here of cells whose vertices will be points in my point configuration, such that they intersect nicely. The union of their convex hull will be the convex hull of A. It's a partition, this kind of property, and it's regular if there is a lifting function such that the idea is I start with my point configuration A, and I can think of this lifting function as adding 1 dimension. So let's think of the plane. We have a point configuration here. I add 1 dimension, and I will give height to all of my points. We can also think of this as a height function. And then when I do this, I start with my point configuration, I give height, then I take the convex hull in this higher dimensional space, and I look at the lower faces, so the faces I see from below, the faces of my point of my convex hull. So there is a precise meaning of what we can see from below. If you remember the definition that faces are the subsets maximized in a direction, it means that we only take the directions such that the last coordinate is negative, but you can keep this image of seeing from below. And then we need just to project down these lower faces, because now they live in a space of dimension. So this lives in r to the d plus 1. We have added this coordinate. And now we just project down to r to the d just by forgetting the last coordinate. So let's look at our examples here. So here we take the whole point configuration. So when do we see all these points from below? One, one way, when I have any point configuration, I can take a trivial lifting function where all the points are at the same height. Then I will see all the points configuration. So I see all the convex hull, but I also see the points inside it. So this subdivision is regular obtained, for example, with this lifting function. This one is when I see these 3 points when I look from below, but not these 3 other points. For example, I can still take these 3 points at the same height 0, and I lift these 3 points at a higher height, let's say 1. I have many choices, but this triangulation, this subdivision, sorry, is obtained if we do the reverse. We take these 3 points that we see from below, and we lift the 3 other ones all at in a parallel hyperplane. So is it okay? Do you see this as obtained as the lifting of the point configuration moment? Cool. And now, can you try to do this one? Maybe you can try, but no, it's not regular. So you can try, but you will never find heights such that the faces you see from below are these ones. Size. Okay, but something. If you take generic heights in general, you will obtain triangulations and not subdivision. What else? In general, like when n is big and at random, we have more non-regular subdivisions than regular ones. But still, first, this lifting construction is a nice way to build actual triangulations, because if I give you the point configuration, and is there always a triangulation? So the answer is yes, there are many with this construction. Okay, and now we will see, we will look at examples. No questions so far.
Did you say in general, if you get any lifting function, you will get a regular subdivision and you will get triangulation?
If I make it generic, meaning that if I move a little my height functions, then I will break the collinearities. So the reason that here we have quadrilaterals is because we have parallelisms, and so if we move a little the heights, we will break this, and we have also there. So a nice example are degenerate divisions. I don't know if anyone knows about them. So the idea is we have a point configuration. Okay, and now I'm drawing a very special subdivision. I will try to convince you why it's special. Okay, so the special property that this subdivision has is that if I choose a cell of my subdivision and I take the sphere that is inscribed, such that my cell is inscribed into this sphere. So, for example, for this cell, I would have a big, let's take this color. Okay, or for this one like this. So the property is that I never have other points of my point configuration inside these spheres. And here is a special case because we have 4 co-cyclic points. So this is why we have a quadrilateral and a subdivision, but if we wanted the triangulation, we have 2 choices in this example. But anyway, so this is the special property defining my Delaunay subdivision, but why would it exist? So the nice thing is that this is obtained as a regular subdivision by taking the lift. That is the squared norm of my point. So in dimension 2, you can imagine that we lift with a parabola, and if we take this height, the faces that we'll obtain have this special property of sphere excluding points, we can say, and it also works in higher dimensions. But this is nice because this triangular subdivision is quite homogeneous. For example, in dimension 2, it maximizes the minimal angle, it minimizes the maximal circumradius, for example. And another nice property is that it's dual to Voronoi diagram. Maybe does this ring maybe a bell more easily. So if I move the drawing here. So the Voronoi diagram is a special partition of the space that tells me, we can imagine, for example, that we have a city with some schools, and we want to say if I take a point in my city, to which school it's the closest to. Okay, so maybe in real life we would not choose the Euclidean distance, but it's not my business, right? So and you partition okay, now I forgot this one. Okay, maybe I missed what happens. No, it's okay. So when I am in this cell, it means that the closest school is this one. The closest point of my point configuration is this one. If I am here, the 4 points are at the same distance. And so, as I hope you can see with my drawing, they are dual. So, for example, yes, this is not very trivial because this point is not inside the triangle, but still we recover the same combinatorics, the same combinatorial information. Okay, so I will not give more details about this notion of duality, but it's a very nice property of any regular subdivisions that we can always find a polyhedral complex that is dual to it. And a nice way to do it is with tropical geometry, but I will not give details just to mention it. Okay, so this was the example with subdivisions and so on. Okay, so let's see. Okay, now I wanted to play with you with just triangulations of polygons. So easy to make drawings and so on. We are just in R2. So when we have 3 vertices, there is only one triangulation. It's the trivial one. When we have 4 vertices, how many triangulations? Okay, everybody. But okay, do the example for 5 or think about it. If anyone knows, you can say it loud.
It's 5, right?
5, yes, great. Still, I will still draw them all, but.
We got the line numbers.
Oh no, you guessed it. Yeah, I thought that it would be a pity to make a combinatorics talk and not talking about the Catalan numbers in Catalonia, even if they are nothing to do with Catalonia. It's just yeah. Okay. So you already know the next one. Okay. So the next one would be this okay. Combinatorics you can ignore the insert. Okay, it's part of that. So let's play a bit with the Catalan numbers. So yes, the property is that the number of triangulations. So there is a shift here. I take n+2 gons, polygons with n+2 edges, to have the nth Catalan number. So how are these numbers defined? So one very usual definition is by induction. So we fix the Catalan 0 to be 1, and then induction is to compute the nth Catalan number. I will have a sum of the smaller Catalan numbers of k. Maybe you need this induction formula. And it's very easy to see why it works with triangulations. So if I want to compute the number of triangulations of my n+2 gon, I can fix a top edge. Then I have my n vertices here, and I will partition the set of all triangulations depending on what is the vertex adjacent to this edge in my triangulations. For example, this one, I say that this is a+1. So here, the number of ways to triangulate this part will be k, because I have k vertices here, and here it will be. So this is a proof that the number of triangulations is counted by these Catalan numbers, and then there is also a closed formula for these Catalan numbers. They are very, very nice. And why do we love them so much in combinatorics is because they count many combinatorial families. So not only the triangulations of polygons, but okay. And there is a book with like more than 200 families, and so we need to find bijections between them, and it's very funny. So maybe I just show an example. Very nice bijection, I think. Maybe this is not the best color. I want it to be green because these are called trees, but I will do them. So the bijection with rooted, because I fix a special vertex here of my tree. Planar, because I differentiate the right and left, so these two trees are not the same for me. And binary trees, because each internal node has two children. And so you see how the bijection works. And so on. This is very cool. Also, people who like more algebra, there is also something nice that we can do here is if we have a binary operation, so we can represent it with these binary trees. So this, for example, this tree means that we do the operation A times B with some binary operations. Here, it means that we first do AB and then C. And here, we are first applying BC and then A. And so sometimes if our operation is not associative, it's not the same result. So we need to keep track of what happens here. And sometimes we can have associativity up to homotopy. Oh, a bit. Okay, and then the same works here. We would have AB from one hand, then CD from the other hand, and then the product. Here we would have CD times B times A, and so on. So this is another family that is counted by these Catalan numbers. The ways of parenthesizing a word of n or n plus 1 or letters. So, and this is cool. And something that is even very cool with these families is that they are not just families of objects. We can put more structure on these families. So, for example, we can put an order and say that this object is smaller than this one. So I put an arrow going upward. So an arrow now, for example, I can see it with my parenthesizing is I move my parentheses from left to right. Okay, so I haven't written down all of them, but you can believe me that the edges will be like this. So another way to see this operation, this arrow operation, you can see them on the binary trees as what is called a rotation, or in the triangulation, it will, or we can obtain them by increasing, by flipping some internal edges of the triangulation, increasing the slope. So for example, from here to here, I flipped this edge, increasing the slope. From here to here, I flipped this edge, and so on. Okay, and we can also do this in this setting. We would have a graph with 14 vertices and these edges, but also we can see intermediary steps. So maybe with the triangulations, the subdivisions is more easy to explain. It's easier to explain. I can say now that this edge is corresponds to not a triangulation, but this subdivision where I forgot this edge of the diagonal of the triangulation. This one would be and so on. And in the middle, we can add also something. Okay, we have no arrows, we have no edges, but we still have a two-dimensional face, which would be the trivial subdivision. And so here, what would we get? And the nice thing is that we would also get a structure that we can see on the polytope. So here it's a polygon, a pentagon. Easy. This is a one-dimensional polytope segment. This is a point. And here we would also have a nice polytope. In fact, one realization of this polytope is this one. So this one has 14 vertices corresponding to the triangulations, or to the binary binary trees, or to the parenthesizing. There are edges for these arrows that I defined, and the five-dimensional structure. And historically, it was not very easy. Yeah, I explained a bit the associativity. This was the part for you. But and so this is the associahedron because it comes from associativity. And it was not very easy to find like explicit coordinates to say, okay, we have to take these coordinates to have this polytope. And now we have many families of realization. So okay, it's super nice, but I will write down the theorem I wanted to write. But yeah, so this is what we have kind of seen, like with this example with the pentagon, and I told you it also works for the biggest polygons. Okay, here I have this notion of refinement that I know that this edge will correspond to this subdivision that is refined by these two triangulations. So is the theorem here? It is nice. Yeah, it's very lovely. Really nice. But then what's the relations with regular subdivisions? Because in fact, what happens for polygons is that all subdivisions are all regular. But so what happens if we do not take these special point configurations that are polygons? If I take any point configuration and not only in R2, but in any dimension, it must be the association, of course. This theorem is almost true. So what is missing is here we need to take the regular subdivisions. And the name here is the secondary polytope. So also this shows why one reason why these regular subdivisions are very special is that if we take the set of all subdivisions, we can always have this refinement order on the subdivisions. But the space of all subdivisions can be wide. For example, we can still have this notion of flip. I will not define it precisely, but there are point configurations such that the graph of all the triangulations with an edge for the flips is not connected. So it's not nicely graded with this, we have vertices and edges and so on. So the topology of this poset is ugly, can be ugly. But if we restrict to the regular subdivisions, then it becomes very nice because the topology of the polytope is nice, it's sphere and so on. And yes, even more than the topology. So yes, this is a very nice result about regular subdivisions, and maybe I skip the third topic, or
we can do 5 more if you want, unless anyone else.
Okay, if someone is too angry, okay, maybe I will say.
End of the bit.
So I wanted. No, I forgot to present this one. So this one is the secondary polytope of the point configuration that we saw with the 6 point labels. And what happens is that these non-regular triangulations that we saw So they are not vertices of the polytope, but in fact they are points inside the face, but they are not given by the combinatorics of the polytope. Okay, so the last topic I wanted to explain a result about the question I mentioned a bit earlier of counting just how many combinatorial types of D polytopes of dimension D with n vertices. So this is a very old problem. Even Euler asked himself for dimension 3, how many polytopes, and so for centuries there were no progress. But now for dimension 3, we know it well because we have this nice characterization with graphs. But for higher dimensions, we only have asymptotic bounds. So asymptotics, we fix the dimension D and we take n that goes to infinity. And why do I? This problem is because it's related to my topic of regular triangulations. So the bounds are as follows. And also some other guy called Alan. Okay, I cheat very slightly now that I consider labeled combinatorial type. So it means I record I put labels on the vertices. So yes, for example, the quadrilateral 1, 2, 3, 4 is not the same as 1, 3, 2, 4. Now I say that in my combinatorial types I can distinguish between these two, but I could not distinguish if I rotate or something. And so the lower bound is so you see that we still have room for improvements, and these are very big numbers. And this we obtain it with my two advisors, Arnau Padrol and Francisco Santos. And the idea, so there is a first step to build so this was a construction by my advisor 10 years ago, and what he does is, if he starts, so it's an induction on the dimensions, and at each step, when he has a polytope, he will choose a permutation on the vertices and take a special lifting. So this idea of we add height, and he does it respecting the permutation in a way. And he needs to do this twice. So he will increase the dimension by 2. So this guarantees two things: that the polytopes he obtains have very nice properties. I will not give details. And very important, we can recover the permutation we chose. So this is why we have this bound. Okay, we can almost recover the permutation, but it's enough to have this. So starting from one polytope, you can increase the dimension by 2 and build factorial n polytope almost, because you can choose the permutations. And very important, you need to be sure that the polytope you build are distinct, are different. But he could do this. Also, when we do a lifting, we add an extra point like at infinity, because we just want to the combinatorics obtained by the triangulations we obtain when we do the lifting. And what we did then is that to show that these polytopes with a very special constructions admit more than all these many polytopes, each of them has many regular triangulations. So if we have a regular triangulation, it means that we can have a lifting as before. And again, we can do this lifting at a point very high, so that we guarantee that if these regular triangulations are different, then the lifted polytope we take, the lifted polytopes we obtain are also different. And so by multiplying these two numbers, this is how we got this improvement. So almost double the exponent. So this is also a nice place where regular triangulations appeared and this lifting construction. And I can stop, and thank you very much for the attention. Yeah.
Are there any questions? Yes. Yes, I have a question. Like, have you studied the bounds, like how hot they are? Like, for example, is there any end for which the maximum is that one? Or...
No, since it's an exponent of the factorial, and it's very bad. And we have no idea if the real answer is closer to square. At some point, my advisor thought that it was this one, but so we disproved it. But it was not a very strong. And to have precise numbers, usually higher than 3. Maybe with small number of vertices.
There is some, maybe I know it's not the topic of the talk, but I was like curious on the vertical geometry thing. Do you have an equation for why the name tropical is there?
The name tropical is for a very bad reason that I think some
I imagine something like that.
But still, yeah. It's a bad name, but